Okay, so let's have a look at a free response question with the calculator. So here we have a table and it talks about a tank having a height of 10 feet. Area of the horizontal cross section of the tank at height 8 feet is given by a function where we have square feet measuring A of H. So I don't know what my tank necessarily looks like. I just know that I've got some sort of tank, right? And the height of the tank is 10 feet. And actually, based on this particular tank, it seems like I have a wider base with the larger cross section and a smaller top, right? So I know that I can figure out, I don't know what it necessarily is, but I can figure out a cross sectional surface area, and I'm given that. Okay, so use a left Riemann sum with 3 subintervals to approximate the volume of the tank. So the volume of the tank is going to be approximately, and here we're using a left Riemann sum. So we need to know the width of our interval and then times the height of our interval. And in this case, 50.3. So we have 2 feet times 50.3 square feet would give me cube feet. Plus the next interval is a width of 3. On the left side is 14.4. And then plus the last interval is the width of 5, and on the left interval is 6.5. And that's going to be feet times feet squared, which is going to be feet cubed. So what I have then is my left Riemann sum with my approximation. It is not necessary, but if I wish to, I can go ahead, come in, and substitute this into a calculator, and I would get 176.3 feet cubed approximately. Okay. This particular problem technically has 2 points, and then there's a third point for the units, but we'll discuss the points later on. Okay. Does the approximation in part A overestimate or underestimate? Well, let's see here. Function A is continuous and decreasing as h increases. So as the height goes up, the cross section is smaller. So that means that I've got this decreasing, right? I've got this decreasing function using a left Riemann sum. And it really doesn't matter how I'm decreasing, right? But that because A of H is decreasing, what we have is an overestimate. Then part C, the area in square feet is modeled by the function. So now we have a function based on this model, find the volume of the tank. So volume is always going to be an integral of a cross-sectional surface area. And if I'm going to be horizontal, I'm going to be using x as my variable. And if I'm vertical, I'm going to be using y as my variable. So I need to figure out the beginning and the end of my interval. Well, my interval beginning is 0 and my interval end is 10. So I'm going to have the integral from 0 to 10 of f of h dh. And I don't need to rewrite it, but I can make sure that I put into my calculator what I need. Okay, so the integral from 0 to 10 of f of h dh, if I put that into my calculator, I would get 101.325338. And I just need to be correct to 3 decimal places, so 101.325, and this would be cubic feet. Then we've got water being pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of this number of feet per minute. Using the model from part C, find the rate at which the volume is changing with respect to time. All right. So for part D, we're working with related rates. All right, and if we're going to be working with related rates, we need to think about what's going to be that implication. So the volume is going to be equal to the integral from 0 to h of f of t dt. All right, so this is how I could describe the volume. Notice, and this is very important, that this variable is h because my final function has an h, and this variable is t because I'm doing this with respect to time. Okay, therefore, let's change this. I can leave this there. The derivative with respect to time of volume is going to be the derivative of this integral from 0 to h of f of t dt. All right, and if that's the case, right, if that's the case, then what I'm going to have is I'm going to have the derivative of h with respect to t, which is going to be dh dt, and I'm going to have that multiplied by f of h, right, using the fundamental theorem of calculus. Now, more commonly, people will write it as f of h times dh dt, okay? And we could also technically say that dv dt could also be written as the derivative of the volume with respect to the height times the derivative of the height with respect to time. We could approach it this way, but I'll focus on the approach that we have here. Okay. So if this is the case, we want this at 5 feet. So I need f of 5 times the rate of change and increasing at 0.26 feet per minute. So I'm going to have times 0.26. And if I use my calculator, that's going to give me 1.694419. And it says to indicate units of measure. So therefore, it's going to be approximately 1.694. And this is going to be a rate of change of volume over time. And it's talking about minutes, so I have feet cubed per minute. So where are the points for this particular problem? The points for this particular problem are as follows. Do I have a setup of finding a derivative? And do I get that derivative correct? And then in the end, do I have my answer correct? So there's going to be 3 points with that. But we still need to pay attention to the units because the units in part D need to be correct. All right. Then part C. For part C, we have our integral and we have our answer. So there's 2 points for part C. But the units need to be correct. So what are we going to be telling you? Make sure you include your units. Then for part B, there's only 1 mark. Do I have the correct answer with the reason? Only 1 mark. And then lastly, we have our Riemann sum. There's 2 marks, right? Did I set up the Riemann sum correctly with the right value? And then we have 1 mark for the units. And generally speaking, that can be a common thing, that your units will be 1 mark as long as all of your units are correct. And then you have the other marks. So please be sure that you're including your units. Okay, so a little calculator-based example. If you have any further questions, be sure to ask. Thank you very much for your time.